is on the counting principle, permutations, and combinations. So we've kind of mentioned combinations before. We used it when we talked about Pascal's triangle, but we don't really know what that is yet. So we're going to learn what it is in this section. So it says much of probability has to do with counting the number of ways that certain events can occur. So for instance, suppose we wanted to know the probability of rolling a 7 with a pair of dice. We construct the following table to help us, where each point in the table has x for the number on the first die and y is the number on the second die. So like I said, we'll do some activities where we're rolling a pair of dice, and I'll make them different colors. So maybe one's a red one and one's a white, or a green and red, or something like that, so you guys can tell the difference between the two. So in this chart, when you see 1, 1, that means you had a 1 on the white die and you had a 1 on the red die. When you see 2, 1, so this 2, 1 right here, that means you had a 2 on the white die and a 1 on the red die. Do you guys see how to read it? So how many total possibilities are there? 36. Why does that make sense, Christian?
Because it's 6 squared, so there's 6 different possibilities for the red die and 6 different possibilities for the white.
Yep, do you guys see it? 6 squared, as he's saying. 6 for the first one and 6 for the second one, so 6 times 6, because every, if you do like a little tree diagram, 1, 2, 3, 4, 5, 6, every outcome you have for the first one goes with every outcome for the second one. I could have 1, 2, 3, 4, 5, 6. Right, you could do it that way. Does it make sense?
For each one you have in the first one, you still have 6 more.
Exactly, it goes with it. So it says, therefore there are 6 different ways of rolling a 7. And you can count it. We could do a 1, 6, a 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. So there's 6 possibilities. So our probability is 6 out of 36, which is 1/6. So the question says, well, what is the probability of rolling less than 5? So how about, let's look at it. How about this one, 1, 4? Is that less than 5?
No.
No, it's equal to 5, right? So that one doesn't work. But the one above it, 1, 3 would.
Yeah.
What about 2, 3?
No.
No. So we're kind of doing this diagonal of 4s, and we're doing this diagonal of 3s, and we're doing the 1, 1 as well. Sum of 2. So we end up getting exactly the same. It ends up being 6 out of 36, which is 1/6. So do you guys think you could construct that table if I asked you to do that? Probably. You could probably figure that out. And there's lots of things I could ask. I could say, what's the probability of rolling an even number, an odd number, something more than 7, something more than 7 or less than 3. Like, there could be lots of questions I could ask. But in the previous example, so in the dice rolling example, it was possible to list the possibilities, right? You could list out all 36 of those options. It's just kind of time consuming when you have to do it on your own, okay? But what if I had 3 dice?
Then it would just be 6 cubed.
It'd be 6 cubed. 6 cubed is 216. Do you guys want to write out 216 possibilities?
No.
Yeah, we'd have like 1, 1, 1, 1, 2, 1, 1, 1, 2. There would be a lot of possibilities, right? We don't want to do that. So sometimes there gets to be so many possibilities that it's really impossible or very tedious to list them all out. Okay, so in order to do that, we use what's called the fundamental counting principle. And the definition is a little bit strange. So it says if E1 and E2 are 2 events, the first event, E1, occurs in M1 different ways. After E1 has occurred, E2 can occur in M2 different ways. Then the total number of ways that the 2 events can occur together ends up being M1 times M2. And I know that definition is a little tricky, so let's try some examples. It will make sense.
It makes a lot of sense when you think about it.
Yeah, if you think about the examples, it's fine. So Cold Stone Creamery has 10 different choices of ice cream, 12 different choices of toppings, and 3 different sizes of waffle bowls. If Edward wants to get a waffle bowl, 1 kind of ice cream, and 1 topping, how many different ways can he choose his dessert? Yeah, Manish, what do you think? It would be 360. And how did you get that? So we took 3 different possibilities for the waffle bowl, and then with that we had 10 choices for ice cream and 12 different choices of topping. And what this is one giant tree diagram. And we'll be talking about tree diagrams throughout the chapter, but basically it's saying waffle bowl number 1, waffle bowl number 2, waffle bowl number 3. So 1, 2, 3. And then from that, I could have the waffle bowl number 1, and I could pick ice cream number 1, ice cream number 2, ice cream number 3, ice cream number 4, all the way to 10. That's a lot. And then each of those branches could have 12 branches off of it. And it ends up being 360 total routes that you could take. So this would be one route there. Does that make sense? It's a lot of routes. So there's 360 total ways of doing this. So the next one says a true-false quiz has 5 questions. How many different sets of answers are possible? And this one is difficult for students to think of. Yeah, let me explain. So the problem that students typically think of is they think it's 10. Because they're like, oh, there's 5 questions, 2 choices for each one. 5 times 2 is 10. Okay, but that's not the way it works. So let's think about a 3-question quiz. I could have true for the first one, true for the second, true for the third one. I could have true, true, false. I could have true, false, true. I could have false, true, true. And what else could I have? I could have false, 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 true, false, true, false, and true, false, false. That's a lot of possibilities. How many do we have? 8. That's just with 3 questions. So for each answer choice, we have 2 possibilities for each answer, for each question. So our answer ends up being 2 to the 5th, which is 32. Yep. So listing out all of the possibilities can be quite tedious. That was just 5 questions. Have you ever taken a true-false quiz that's 5 questions? Probably not. They're usually a lot more, right? So how about this one? So a multiple choice quiz has 7 questions, each with 4 possible answer choices. So these 7 questions, 1, 2, 3, 4, 5, 6, 7, have 4 possibilities. So how many different sets of answers are possible?
16,384.
How did you get that?
I did 4 to the 7th.
Yep, exactly. So each one has 4 possibilities. Each of those possibilities goes with each other possibility, so it ends up being 16,384. That's a lot. Can you imagine if you walked into a classroom, like let's say you're in Spanish 3, and instead you walk into the French 4 final, and you have no idea what's going on? You're like, why is this whole thing in French? This is like a dream, like a nightmare, right? Have you guys ever had this nightmare where you forget to show up for your final? Yeah, so can you imagine taking a test in Russian or something that's totally not familiar, and guessing? The probability of you getting every question right on that would be 1 out of 16,384.
If it has 7 questions.
If it had only 7 questions, right? And a final with only 7 questions, probably not going to happen. All right, so an exam has 10 multiple choice questions with choices A through D and 5 true-false questions. So if I have choices A through D for the first 10, it means I'm going to have 4 times 4 times 4 times 4. How many times? 10 times. And then the true-false questions, what am I going to have there? Yeah, I'm going to have 2 to the 5, right? So I'm going to take my 4 to the 10 and 3 to the 2 to the 5, and it ends up being a number that is very pleasing to me. I don't know why I like this number so much. 3, 3, 5, 5, 4, 4, and then it sadly is 3, 2. Shouldn't have been like 2, 2. Wouldn't that have been fun? It would have been nice. I like nice numbers. All right, so 33,554,432. So back when I was in high school, we didn't have much to do in good old Muncie, Indiana. And we used to kind of drive down the one street that's in Muncie, Indiana, which is McGalliard. And we used to try to like wave at people we knew. Cruising, that's what they used to call it in my mom's day. But it was always kind of fun because when I first learned how to drive, and we would drive on like Highway 69 or somewhere, we would see different cars and we would know if they were from Muncie or not. And we would say, oh, do we know these people? They're from Muncie. And then we would pull up next to them and we wouldn't know them, but we would at least like peek in their car. And the reason that we knew they were from Muncie is because license plates in Indiana used to be a certain way. Do you guys know this?
They still have.
They still kind of do at the very bottom, right? So back in the day, when I was from Muncie, Indiana, my license plate always started out with 18. And then I had a letter, and then I had 4 numbers after it. But that 18 represented the 18th county in Indiana, which was Delaware County, 18th alphabetically. And Marion County was 4, 9, or 4, 9. And then it had a letter, and then it had 4 numbers after it. Okay, so every time we saw 49, we were like, oh, those people are from Indianapolis. Okay, but we did away with this. I really thought it was cool. I really liked having that because I could see, you know, even if I was way down in Evansville, I'd be like, oh, there's an 18. That person's from my hometown. They're from Delaware County. I wonder if I know them. And we don't do that anymore. Okay, so let's talk about why we don't do it anymore. So it says in 2007, a Marion County license plate began with the numbers 4, 9, and then had a letter followed by 4 other numbers. If the letter could be any letter in the alphabet, so let's say we have a letter here, and then we have 4 numbers that are 0 through 9. So how many choices do I have for the letter? I don't know why I did a big box around it. Yeah, I have 26 choices for the letter, right? 26 letters in the alphabet. Maura used to ask me that every year. She'd be like, how many letters are in the alphabet? 24 or 26? I'm like, 26 are in the... All right, and then 0 through 9. How many possibilities are 0 through 9? 10, not 9.
Because of 0.
Yeah, because if I had 1 through 9, that'd be 9. But I have 0 as well. So I have 10 choices here as well. So I end up doing 26 times 10 times 10 times 10 times 10. And my total number of license plates that I could have is 260,000, 260,000 license plates. Okay, so it says, do you think this is an adequate number of plates? I don't know, it could be, maybe, for Marion County. I said the approximate population of Indianapolis, Marion County, is 782,000 people. Do all the people drive?
Well, almost everyone.
All the people don't drive, but some people do have multiple cars, don't they? Those people that have like 10 cars in their garage.
You say that the average person has all one.
So I don't know. I don't know if it's enough, but actually I do know that it was not enough because you know what they did with the license plate thing? Is they started giving, do you guys know how many counties there are in Indiana? No, there's 80 something.
Those 90 something.
Yeah, maybe 90 something.
Those 92.
I need to look it up. Yeah, so in Indianapolis not only had 49, but they had 99, 98, 97. They started going backwards. And then there was another county that caught up with them. Do you guys know what county would have caught up with them? Nope. Well, Hamilton probably now, but it was first Fort Wayne. So Fort Wayne had a population that was too big as well. They were 2. All right, so an ID code consists of 2 of the digits 1 through 5, followed by 3 letters from A, B, C, and D. So imagine you're going to work and you're putting in like a little code on the door or something, and there's letters and there's numbers. Okay. So we started out with 2 digits that are from 1 to 5, and then we're going to have 3 letters that are A through D. And it says you are allowed to repeat the letters or numbers. So you could have 22 ABC, or you could have 1, 2 AAB. That's fine. So I have how many choices for the first slot? 5, 5, and then I have 4, 4, and 4. So when I multiply those all together, I think I get 1,600. Is that right? Yep. Okay, so you know since I put something about how I can have repeats, that the next thing's probably going to say I can't repeat. And really, this is what we do to make our passwords safer. Because if someone gets like your ATM card, you know the first numbers they're going to try? 1, 2, 3, 4, or 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. Those are the first things they're going to try in the machine, right? So we often make stipulations that ID codes or passwords can't have repeated numbers or letters. So this one says we can't repeat the numbers or letters, so we still have 1 through 5 and 1 through 5. And we still have A through D here, but we cannot repeat. So how many choices do I have for the first slot? 5. Once I choose that number, I have 4 left, yeah. What about the A through D?
4,
3, 2.
Yeah, it goes 4, 3, 2. Exactly. Does that make sense? Do you guys get that? Because once I choose the number or the letter, let's say I choose C, then I can't use C for the next one. So now I only have choices of A, B, and D. So there's only 3 choices and then 2 choices. What do we get when we multiply this? So that's 480. Awesome, thanks. All right, now it says repeat example 6, but now make the additional stipulation that we cannot repeat letters, but we can repeat numbers. So maybe the letters are bad, but the numbers are okay. So if you can repeat the numbers, what do we start with in the first 2 slots? 5 times 5, yep. And then we can't repeat letters, so 4, 3, 2. Yep, exactly. Okay, so now we're getting to what we call permutations and combinations. Math vocabulary, gotta love it. All right, so for convenience, I'm gonna call permutations, when I talk about permutations, I'm gonna talk about some different things. I'm going to talk about places, positions, and things like presidents. All P words there. So places, positions, and presidents. All right. If you're running for class officers, I know we don't have class officers, we have stewardship at our school. But back in my school, we had class officers. I was the class treasurer because I was good at math. But let's say I was running for treasurer, and for some reason I got elected president. Do you feel like that's wrong? Yeah, so positions matter. Like, it matters who's put in each position. That's the order matters in that case. So for these ones, the order matters. But for combinations, this is things like clubs, committees, things like that, like groups of people. This is where the order doesn't matter. So if I was picking a group, let's say Greta wants to pick people to help her with Cluck Webster after school. And she's like, hey guys, come out for it. Is there a name of the club? Poultry Pals. I did not know that. That's a fun fact. Come out and help me with Poultry Pals. And I'm going to select a group of you because, you know, we can't have 200 and something number of Poultry Pals. We can only have 5. That would be a combination because you're just saying, I just need a group of people to help. But if she was deciding with Poultry Pals that she needed to come up with a schedule, do you see how that might be different? So if she's like, okay, Poultry Pal number 1, you're going to be Monday. Poultry Pal number 2, you're going to be Tuesday. Does this make sense? That would be like a permutation. That's where the order matters. Okay, so there's a slight difference. Okay, which one do you think will have more possibilities? So I think on this next page I start talking about A, X, Y, Z, and so on. I usually talk about my nieces and nephews, Eleni, Bridget, CJ, and Devin, because they have Eleni, Bridget, A, B, C, D. But let's say we have these letters. So X, Y, Z. And it says, suppose I want to know how many different ways I can arrange these letters X, Y, and Z. Well, I could have X first, Y second, Z third, or I could have X first and then Z and Y, right? I could have Y first and then X and Z, or I could have Y first and then Z and X. And I could have Z first and Y and X, or I could have Z first and then X and Y. So how many ways to arrange 3 different items? 6 ways. That's exactly what we've been doing. We've been saying 3 times 2 times 1, right? 3 letters could go in the first spot. Once I choose that letter, I only have 2 choices for the next one, and then 1 choice, a total of 6 ways. But if I had A, B, C, and D, Eleni, Bridget, CJ, and Devin, my nieces and nephews, and I wanted to choose 2 of them, and let's say we were, I think I give an example on our probability activities where one of them was going to choose the activity that we did. So they got to choose, hey, we're going to go to the Children's Museum today, Aunt Jenny. And one of them got to choose the restaurant that we went to, right? My nieces and nephews are going to be mad if one of them gets to choose something and they wanted to choose the other one, right? That order matters because I'm saying you choose this and you choose that. Does that make sense? So in that case, I could have A, B, but I could also have B times B, comma A, right? Does this make sense? Or I could have B, C, and C, B. How many do you think is going to be possible there? Why do you say 24? It ends up being that 4 times 3 times 2 times 1, right? That's where the order matters. So this would be permutations. But what if I didn't want the order? What if I just said, hey, 2 of you, you're going to be the 2 nieces and nephews I like today. You get to hang out with me today. The rest of you, you just get to hang out with your mom and dad. 2 of you get to hang out with Aunt Jenny. We're going to have a fun day. Then Eleni and Bridget is now the same, right? Do you guys understand what I'm saying? AB is the same as BA. So you would just have how many possibilities? 12. So we've divided by something. We got rid of the number of repeats. How do we get rid of it? The number of ways that I can repeat 2 people is 2 times 1. I divided that out. Does it make sense? So it's kind of weird. So permutations and combinations are similar. Permutations ends up being a bit more. So this is the bigger number. And this one we divide by repeats. So their formulas are similar. So for permutations, which I might see as Pn, R, or NPR is on your calculator, we'll say that. But it ends up being n factorial divided by n minus r factorial. And combination starts out the same way. So I still have my n factorial over n minus r factorial, but I divide out by the number of repeats, which is an additional r factorial. So that's what's on our denominator there. So r factorial is there. And like I said, in permutations, the order matters. Okay, so I know that's a lot of explaining there, so we're going to do some examples. I know it's really weird when you first learn it. Yeah. Yeah, so it says, how many ways can you arrange the letters, what were the letters A through F? So how many ways can you arrange the letters A through F? You can continue to still do the slot method. Permutations are really just the slots. So permutations could use slots. I call it the slot method because I'm filling slots, like this slot, this slot, this slot. All right, so it ends up being, how many letters do we have?
6.
6. So 6 times 5 times 4 times 3 times 2 times 1, which is 720. 720. All right, that is the same if you go to your calculator and you do 6p6. So I'll show you on this calculator. I would put in 6 first on the calculator, so you can try it with me if you have your calculator out. So I'd put 6, and then I do math, go over to PRB, NPR, 6, and it tells me 720. It's also the same as 6, math, go over to PRB, factorial, right? Same thing. So how many ways can I arrange 3 of the letters? Well, what if I only have 3 of the letters? 6 times 5 times 4, which is 120, yep. That is the same as 6 permute 3. It also, the formula ends up being 6 factorial over 6 minus 3 factorial. So it's 6 factorial divided by 3 factorial. So think about how this is related to what I'm doing here. 6 positions, I'm filling 3 of the slots, right? What happens to the 3 factorial? If I had 6 factorial divided by 3 factorial, yeah, exactly. It's 6 times 5, 6 times 5 times 4, 3, 2, 1. And Julian's saying, oh, that last part, it just goes away. It gets canceled out anyway. That's why it ends up being 6 people in 3 slots. That's the way I think of permutations. 6 people going in 3 slots. Did you get it? So how many ways can I create a group? I did not use the word arrange this time. Arrange means order matters. It means I'm putting them in a certain order. If I'm creating a group of items, then if I have ABC, it's the same as BCA. It's a group. So what do we do here?
Well, you just do 6 cubed.
We do 6 with a combination. So C, 6, 3. So 6 choose 3 is how we read that. And on your calculator, it's right where NPR was. So it's 6, hit math, go over to PRB, NCR 3. So it ends up being 20. Now, of course, I will do a calculator test and a non-calculator test on this. And I expect you to know how to do that without a calculator. So there was a formula that I gave you. And the formula is helpful. You can know the formula. However, there's a shortcut to doing it. So the first thing you do is you think about a permutation. So combinations are related to permutations. They're similar. So if I was doing 6 permute 3, 6 people, 3 slots, how would I do that? 6 times 5 times 4, and then I divide out by the number of repeats. Well, what I just said is that ABC, that set of people, Lainey, Bridget, CJ, how many ways can that be written? ABC can be written as ABC, ACB, C, A, B. 6. How are you getting 6, Elise? 3 times 2 times 1. So what you do is you divide by the number of ways you can arrange those 3 items in the group. You divide out by the repeats. You say, oh, I just want that one time instead of 6 times. And so they line up. So whatever you have, 6 times 5 times 4, you're going to have the same factorial below, like 3, 2, 1. It's going to go all the way down to 1 down here. And then you start reducing out. Well, 3 and 2 make 6, so we cross out that 6. So we get a total of 20. So all of you guys can do that without a calculator, I promise. We'll do lots of them. All right, so 6th, 5th grade students are competing in a spelling bee. In how many different ways can they place? What's the key word here? Place. Does the order matter? 6 is a key word too, I guess. Does the order matter? Yeah. I'm going to be really mad if I'm in 5th grade and I win the spelling bee and they give me the 6th place ribbon. I'm like, I won that spelling bee. Give me my right ribbon. I got first. So it matters. So we have 6 times 5 times 4 times 3 times 2 times 1. So again, that's the same as P 6, 6. 6 people, 6 places, we get 720. So Allison was given 8 choices in her art class for an assignment. She is to choose 3 of them, all to be due on Friday. How many different ways can this be accomplished? So is it a permutation or is it a combination? Does the order matter or does it not matter? It doesn't matter. Why does it not matter for Allison? They're all due on the same day, right? It's not like you're saying this one's due Friday, this one's due Monday, this one's due Tuesday. She's turning them in as a group all on the same day. So this is going to be a combination where we do 8, choose 3. So let's see if we know the shortcut. So you could use your calculator, or you can say 8 people, 3 places. So 8 times 7 times 6 over, number of ways we can repeat 3 people. 3 times 2 times 1.
Why is it always just the top? Is it because there are 3 people in total, or?
Yeah, in the formula, it's 8 factorial over 8 minus 3 factorial, and then we have an additional 3 factorial. So when you start out your 8 factorial, you have 8, 7, 6, and then the 5, 4, 3, 2, 1 ends up canceling with the 5, 4, 3, 2, 1 on the bottom. So that's why it ends up being kind of like a permutation at the beginning. It's saying how many total outcomes can I have, any order, where the order kind of matters, but then we divide out by those repeats. So we say, well, 6 of those are, every 6 is exactly the same group. Like ABC is the same as BCA, which is the same as ABC. So we have to divide by the number that we repeated. So that's why it ends up canceling. So that's the shortcut. So we get 56, and you can use your calculator there. You'll see it's 56. This next one is hard to do without a calculator. I'll let you use your calculator. So it says 15 students are interested in an upcoming community service event, but Mr. Morrison, he says, hey, I got enough people with community service. I can't take any more. Can you imagine? He says he only has room for 6 more students on the bus. So how many different ways can he choose these students? So it's a combination. Do we see why it's a combination? Yeah, it doesn't matter if he chooses them first, second, third. They all have the same job. They're all going to the same event. It's not like he's saying, you're going to help at the orchard school with endangered species, and you're going to help at, like, he's not giving them exactly like a certain job. So this one's harder to do without a calculator. So we do 15, we go over to NCR, 6, it ends up being 5,005. Yeah, Greta?
So when you're trying to decide what goes on the bottom, is it just like she is to choose 3, so there are 3 going, 3 not?
What do you mean? What, the number that goes on the bottom?
Yeah.
Oh, like
3, 2, 1.
Yeah, so in the Allison's art choices, let's say she had art choices A, B, C, D. So Tasha gave her all these art choices. The first thing we do is we pick those 6, or I guess 8, G, H. We have 8 projects, and we need to select 3 of them. So that's where the 8 times 7 times 6 thing comes in. That would be where the order matters. Like if you're saying, oh, you have to do A first, and then you're going to do E, and then you're going to do F. Okay, but we don't want the order to matter. They're all due on the same day. So we take that and we divide by the 3, 2, 1, which changes it so that you're saying, oh, well, that group A, E, F is really the same as F, E, A, which is the same as A, F, E, which is the same as you divide out by the number that you repeated by. Because you had too many possibilities. It's like this example where we divided out by this column. You're like, oh, that column was all the same. Okay, so we just got rid of it. All right, so how about the next one? What'd you guys get for the next one? Number 5. So 12 countries competing. How many different ways can the gold, silver, and bronze medals be awarded? 12, choose 3, so it's going to be 12 times 11 times 10. So 1,320.
I mean, I didn't realize I thought we were supposed to do more.
Yeah. All right, so let's get to the tricky one. So it says, again, if Cold Stone Creamery has 10 different choices of ice cream, 12 different choices of toppings, and 3 different sizes of waffle bowls, how many different ways can you create a dessert with 1 waffle bowl, 2 types of ice cream, and 2 toppings? And I messed this up when I first started teaching, and a lot of teachers mess it up every single year because I tutored this a lot. And I learned the error of my ways, and other teachers just did not learn the error of their ways. Because the way that I first taught this, which is wrong, I should have realized it was wrong, is I did waffle bowl, ice cream number 1, ice cream number 2, topping number 1, topping number 2. I did 5 slots. Yeah, but I only have 3 slots here. And the problem is, if you go to Cold Stone and you say, I want, let's use their basic toppings, or their basic ice cream, chocolate and vanilla. Is that the same as getting vanilla and chocolate? It is. Right, so if I did all the choices of ice cream, just ice cream, you would think it's 10 times 9, but it's not. There's not 90 choices for ice cream. How many choices for ice cream are there? What'd you say, 5? No, not 5. No, not 15. Not 10. Nope. 10 times 9, but we have to divide out by the repeats, right? Chocolate and vanilla is the same as vanilla and chocolate. So what am I dividing by? 2. I'm dividing by 2 times 1, right? 2. So it's really 45. So what I'm doing in here with the ice cream is I'm saying I have 10 choices and I'm selecting 2 of them. That's why we read it as 10, choose 2. We have 10 items, choose 2 of them. And same for toppings. I have 12 items, I'm choosing 2 of them. But the waffle bowls, I mean, you could write 3, choose 1, but it's actually the same as 3. 3, choose 1 is just 3. Now we multiply those together, so we get 3 multiplied by 45, multiplied by, can anybody do 12, choose 2 in their head? 12 times 11 divided by 2 times 1, 66. So we have 3 times 45 times 66. So we get 8,910. All right, so we have some more examples, but we'll stop here for today, and then we'll finish